The industrial DevOps movement, they have a great book out. As I mentioned, it's completely adjacent to innovation. But over to you, Suzette and Robin. Let's give them a big hand.
Thank you. All right. So thank you for being here. We appreciate this opportunity. I'm Suzette Johnson. I work for Northrop Grumman. I am an NG Fellow at Northrop Grumman. Been there for a little over 20 years now, and have moved from primarily large software systems to cyber physical systems, focusing primarily in our space sector, which is like the coolest place to be. And been doing Agile since actually May 2005. Pretty specific. I actually know exactly when that transformation started and that journey. So I continue to lead our Lean Agile and Lean Agile integrated with digital capabilities practices within our company.
Awesome. My name's Robin Yeman, and I am currently at Carnegie Mellon, the Software Engineering Institute. But I met Suzette while I was Senior Technical Fellow at Lockheed, right? And so we would talk, we would run into each other at different conferences, run into each other at different events, and feel like we had the same story. Because everything that you build, everything that we build, is huge, right? And so the first thing that we had to learn how to do was, how do I scale it? What happens when I have more than 7 plus or minus 2 teams, or people on a team? And how many teams do I have, and how do I communicate, and all of those things? And then what happens with cyber physical? I've got long lead times. So we spent quite a long time. We've been working with each other for at least a decade, probably more, talking about all of these same things. And we're hoping to bring that to you today. But feel free to jump in, ask questions.
Yep. So our topics, before we jump right into the content, we want to give a little bit of context. We're going to have to do so a little bit of definition about what industrial DevOps is, and we'll talk about those principles. And as we talk about that, we'll move into the area of digital twins and touch a little bit on AI and some steps for getting started if this is an area of interest to you.
All right, so I usually tell people one of the things that I want to do is use all the tools in my toolbox, right? So I'm a huge fan of Agile. I had my first Agile program in 2002, and I knew almost nothing. But I'm also a huge fan of model-based systems engineering, and I'm quite fond of augmented and virtual reality. And I think that things like digital twins help, and shift-left testing. So how do I bring all of the tools in my toolbox together in order to deliver systems, we usually say within the government space, at the speed of relevance?
So as we were on this journey of thinking about what does it mean to apply Lean, Agile, DevOps, these emerging digital capabilities, systems thinking, some of the systems engineering practices all together to build cyber physical systems, and what would those principles look like? So as we define these 9 principles, we actually worked with industry. We started in 2018 actually collaborating, writing papers, working through what we think this means, and that way we got a larger perspective, not just in the aerospace, but also automotive and other industries as well, so that we could validate our level of validation on these 9 principles. So we'll talk briefly. This presentation is not about these principles per se. What we're going to do is talk about how we use digital twins as an integration to support these principles. But just touching on them quickly, the first one is how do we visualize and organize for the flow of value? So if you think about it, we're building really large systems, and historically they've been functionally siloed, software, hardware, embedded, integration and test team way over here that we don't see for 6 months. But so what if we were to actually organize these people instead of functionally, but around the flow of how we actually build our system so that they can actually integrate their capabilities and their system along the way? And what does that look like? So that's where we focused on our first principle. Our second one is around multiple horizons of planning. And this is really important as we build big systems.
Oh, see,
Yep,
I'm
go
just
ahead.
dying to
ahead.
interrupt. No, so I'm a huge passion, or have a lot of passion around this one because we talk about, you know, I don't know what you call them, but people that are very stuck in, let's say, hey, in Scrum we only plan for 2 weeks at a time. We never plan forward. In Waterfall, we have an integrated master schedule, and you can tell where Robin is in November of 2026 in the 3rd week on a Thursday, right? Because somehow we have invented that and we figured it out. And so one of the things we really had to focus on with our teams is to bring that together. So I want to use empirical planning, but to get to like the moon, right? If we're going to get to the moon and then get to Mars in 2030, I have a long-term plan. I have a vision. I have a high-level set of objectives, and then a series of experiments or things where I'm gathering empirical data. So I'm going to use those 2-week, 1-week, whatever those sprints are, and I'm going to use that to inform my plan. And you may go, how is that different than your integrated master schedule? Well, I don't know if you guys have had this experience, but because the integrated master schedule is on paper, it's actually really in concrete, right? And we add it as a part of our contract. So even when we learn new data, God forbid we decide to change the IMS, right? What we want to do is beat people till they get back on that IMS. And so we really call it the difference between predictive planning, where's Robin in 2026, versus empirical planning. What has the data showed me, and where am I really?
Yeah, and then principle 3 is all about making data-driven decisions. So we have 2 perspectives of that. One perspective will be the demonstrations that we're used to in our agile process of demonstrating working features or working functionality. It may be in a physical environment, or because we're building cyber-physical systems, we might be doing those demonstrations in models. But at the same time, we're actually using real-time data. We could be getting data from our digital twin that we'll talk about shortly. It could be the data on actual real-time progress of how our teams are doing. It might be real-time data that we're getting out of the factory so we understand how things are evolving across the factory floor, or some dynamic scheduling because we don't have all the parts we need for A, so we're going to go work on parts B. And we can use all of those digital tools to help us make these better and more informed decisions.
The next one's architect for change and speed. Now, I think most of us know that, right? We need modularity, right? But context matters. So a good example is there was a couple years ago, because I was a senior tech fellow, and they put you on red programs, that's what you get to do, where I was sitting in front of the Defense Innovation Board, so the DIB, and they were yelling at us, Lockheed Martin, about the F-35. I mean, of course, there's problems. So the Defense Innovation Board is made up of folks from Google and Amazon, et cetera. And one of the gentlemen from Amazon, who I'm pretty sure was younger than my son, and I don't mean this offensively, but I'm pretty sure he was, said, I don't know why you didn't build the F-35 with microservices in the first place. I don't know. In the 90s, when it was designed, I don't know why we didn't think of that. And then, oh, by the way, it is a real-time embedded system, so there's definitely some things that I might want to take into context there, right? So microservices are awesome. Are they for everything? Maybe, right? But context matters. So we want to architect for change and speed, but we actually want to think about it.
Yep. So 5 and 6 actually go together, and that's, you as an Agile community, you are probably already familiar with 5 and 6, which is the importance of iterating and kind of learning as we go, kind of build fast or fail fast, fail early, recover quickly. And of course, we're going to do that on cadence and synchronization. So, and all about flow, right? And that kind of ties back to that data-driven decisions. We need to be measuring the flow of value across the system, which is not just how fast stories are getting done and how quickly we're iterating on those stories, but how fast are we actually iterating on integrated working system capabilities.
So, you know, the last up, well, not last up, but shift left, right? Shift left everything. So I don't know if you guys saw Dr. Will Roper's Dev Star, which I thought was fantastic. And the reason I think it's fantastic is because he said, DevSecOps, cool. he's like, dev automation ops, dev integration ops, right, all the things. But basically beginning with the end in mind, all right? So typically, I can tell you, I've built lots of systems over the years. We find out that we're off track the first time we try to integrate it. It's a given, right? Instead of this, hey, we've got to build security in, I've got to build test in, I've got to build airworthiness in. So I'd say begin with the constraint. And then I think you got last up.
Yes, and that includes manufacturability, which is the kind of uniqueness for cyber-physical systems. And then the last one is apply a growth mindset, right? We think we've got it all figured out. We never have it all figured out. And we need to recognize that so that we can continuously improve and make sure we're getting feedback from our sort of agile teams, and we want to ensure that we're providing these safe environments to make these improvements. Okay, so that's the highlights.
All right, so what's a digital twin? Interestingly enough, just like everything else, we have a different perception across everybody, right? So language matters. Now, typically, I look at it from I've got a physical asset, I have a cyber physical asset, meaning I've moved that into digital space. What's the benefit? Well, by moving that into digital space, I can learn faster, I can iterate faster. It's just like the first speaker talked about Sam Altman. He says, you know, how can you iterate faster? Well, it's a heck of a lot easier to iterate in digital space than it is in physical space. Doesn't mean we don't need to do all that, but that is the benefit.
Yep, and that's specifically important for cyber-physical systems, right? Because the cost of change and the cost of iterating is lower in the virtual space, which is why these principles are actually being able to be implemented in cyber-physical systems now because of the emerging digital capabilities. So building, I'll start. And,
okay.
Yeah, we got it all planned.
We're not winging it.
Yeah, so we created this slide. Actually, it was Robin's enlightenment here, because we were talking about people are really confused about what a digital twin is. They're talking about digital twins, and what they really mean is they have a digital model or a digital representation. But is it really a digital twin? Just because you have a digital model, it doesn't mean we're actually able to send communication and get real live updates between the physical object and the virtual object.
And so the reason I like to brief this is because I'm waiting for somebody to tell me I'm wrong, because we kind of made this up, and I could be wrong. But one of the things we tried to take a look at is, okay, so I'm beginning with a prototype, and that's a manual data feed, right? If I want to do a simulation of, let's say, an orbital adjustment, whatever, I can simulate that. The digital model, I would say, hey, we've got a manual feed both ways. I can do a manual feed to the physical system, and I can take that telemetry and manually feed that back to, right, the model. When we get into simulation, I'm also doing this manual feed, but it's usually a one-way. I'm usually taking telemetry from the physical system and I'm pushing it back. There's terminology out there called digital shadows. It's in some places, and other people call it something else. But again, digital shadow is kind of a low-fidelity model with some real-time telemetry being sent to the actual cyber-physical system, but it's all manual back to the main system. So according to Greaves, he would say a digital twin, and he's kind of one of the first people that's been writing about it. He would say it's real-time physical, automated telemetry coming from the system and back, right? So it's a two-way. So when we talk about digital twins, that's what we leveraged is Greaves' work. However, just so you know, nobody agrees on all of this. So we're just giving you, the one way.
Okay. So some applications of this. Some of these things you might already be familiar with based on what you read or what you might see even in some news articles. about how we're using it in manufacturing or even urban planning, right? So smart cities, everything has sensors now, so we're able to get that real-time data. We get it into a digital twin. We can actually make changes, and we can actually use machine learning to make those changes, and it pushes out and might change the timing of stoplights or things like that to actually help traffic flow. So there's these emerging capabilities that we're seeing with digital twins in manufacturing, urban planning, automotive, aerospace. Agriculture was another area I've been looking at recently with some projects I'm working on. So it has a lot of ability or possibilities of where we can apply this, so that, and it's all about the learning, right? But you have to have the real-time learning from the environment, whether that's your physical system into your digital system, and then making sure the communication and updates are happening both ways.
Let's see. Yes. So artificial intelligence, where does this come in? Well, our speakers before were fantastic, so I'm not even going to try to go beyond that. But here's the thing. One of the things you probably realize as I talk about digital twins and physical system and cyber physical system is the huge amounts of data and emergent behavior that happen in complex cyber physical systems. So we know that the benefit of AI can really help support those complex systems, meaning I can test emergent behavior. One of the things that Tesla has talked about is their digital twin ecosystem. And basically, they've got a digital twin of each and every car, and they aggregate that data. I can't even imagine how many servers and things that takes, what kind of compute power. But anyway, they aggregate all that data, and they're able to predict emergent behavior because they've got the large numbers as well as those systems. So this is where AI is really going to push us forward. And here's just the different types of AI, and there's more. We've been playing with generative AI, which is super fun. That's usually what we call ChatGPT. So when I take a look at that, how can that help me? Well, one of the ways it can help me is it actually can improve my systems engineering. I don't know about you guys, but I have never seen a requirements document that really looked exactly like what the customer's intent was, and it's because mind reading is a bit difficult, right? So we can definitely, I love that approach of, hey, you can put it into DALL-E and get an image or a representation, something to get us on the same page. We want to take that continuous learning and expand it. So just like Jim and John were saying, what's an extension of the manifesto? We don't think it's something different, but we want to extend it to the system level. Because if I get my software done really fast, it doesn't actually, in our case, right, it doesn't get the B-2 bomber out there faster. I need all of those pieces coming together. So leveraging the intersection of continuous integration, agile systems engineering with a cyber physical system, all the tools in your toolbox, allows us to build that faster. You want to go with it?
This is like improv, sorry.
Yeah. Well, it's not, because my son does improv, and he's really good at it.
Sorry,
they make fun of stuff.
It's a slide that just got dropped in here. Go ahead, you're good.
So these are the benefits, right? I don't want to harp on them, but these are the benefits. They all come back to exactly what the first speaker said is, or actually what Sanjeev said, which is go faster, right? The company that learns the fastest wins.
Yeah, so we have some use cases that we go through in terms of looking at how it's actually being applied in our context in the aerospace community. And we can look at how we're getting that real-time data. We can use it for mission planning, wargaming, understanding what's happening, getting the feedback from the satellite constellations to make decisions. So one of my projects I'm working on, we're actually looking at this type of technology, like I was mentioning, for agriculture. And it was really interesting, like how the world of farming is changing dramatically because they're actually able to get the data from the sensors, from satellites, and now farmers can actually sit at their machines and figure out, do I need to go irrigate? Do I need to change, the pesticides, or what's going on actually in my fields? So I think the application of this is so so broad and just touching every industry.
So organizing for the flow of value, I was talking to this lady that works at Siemens Health and Ears. You know, I'm talking about digital twins. She's like, yeah, we're talking about digital twins for humans. All right, so let's say I want to try a new drug, or I want to do surgery, or you can have a digital twin of people, and you're drastically reducing, right, you know, any kind of interactions, because they got a model of you in cyber physical space. I was like, okay, mind blown. But huge that we can leverage that. And again, you know, that multiple horizons of planning, we talked about it before, but it's that integration of using real-time, near-term data to provide and improve upon that long-term planning, right? So empirical planning.
And I'm so glad that we have the principle of improving and implementing data-driven decisions, because I think that is the one principle that comes up almost all the time around these enabling digital capabilities, because it's providing the data that we need to make better, more informed decisions. So there's the, you know, the hospital with the patient, or again, it could be on my manufacturing floor. There's just all these different opportunities of when do I need to make change. So we were talking about Tesla, right? And as they're aggregating information, they can do predictive analytics. And based on that data, they can know whether your battery is about to die, right? And you get that feedback, and you know you need to go make some changes.
Usually I just find out when I can't start the car. So getting started, there's a whole bunch of things to getting started, but begin with why. What are you trying to do? What's the outcome? Identify, you know, what are the challenges? What are the goals, right? We talk about begin with the end in mind. We're really a big fan, and we didn't touch upon it here, in MVP, minimum viable product, and MVP. Drastically misunderstood within the government space often, because they do think that's deployable. However, you know, when the book was written, Lean Startup, he really said the minimal amount to learn from, right? Which may not be a deployable object. Really focusing on the infrastructure. One of the papers that we're currently working on is how do we get people to invest in digital twins? They're not cheap, right? This is an expensive thing. When I was talking to some folks at NASCAR, they said, you know, typically we have to crash a car, and we have to crash into the, you know, the different environment that it's in order to evaluate safety, security, where the problems are, or where the potential security and safety points. But now they can do it via digital twin. They can crash the car many times. Okay, so it typically costs them a couple million to crash the car and environment in real life, and it still costs them 100,000, but they can do it a lot more often in digital space. So it's not free. What's that break-even point? When should we go there?
As we said, we've been on this journey for quite a while. Our last paper actually was just released this week, and that is what we were talking about today, applying the digital twins with these agile and lean practices and industrial DevOps.
And if you take a picture of this, you can have a free chapter of industrial DevOps. And if you reach out to me on LinkedIn, I got some digital copies too. Content here has been fantastic, yes. So I'm pretty sad about leaving. But I wanted to give you something to take away. And I think that's it.
Principle number 3, data-driven decision-making. What about the other side of decision-making, the intuitive side? Because there are really two systems that we have in our minds for decision-making. One is sort of the practical, rational, long-term, and the other one is intuitive, short-term. How do you get that involved?
So a good point, and I think when I hear that, I think about that other book. Obviously, I read too much, which is the slow and fast thinking, because you're absolutely correct, and I think that needs to be put in here. I think part of the reason we were so passionate about the data-driven is because you'd be amazed at how many decisions are made within our corporations where they haven't actually looked at any of the data, but they're like, I think this would be a great idea, let's do this. But they're both equally important. So definitely something to add in here as well.
There you go.
All right. Thank you guys. Really appreciate it.